Alright, so section 5.1 is all about the beginning of the integral, and the idea of what an integral does for us. So again, this is part of the how come. It's the idea of where do we use these for, what do they do for us. So the integral of a function, we're trying to find the area under that function. And when we say area under, we mean between the x-axis and up to where our function is. Okay? So a couple of things. We're going to talk about why would we do this, and then we're going to talk about a few other things about it and how we can get to it. Okay, so that's number one. We're trying to find that area. Someone might well ask, well, why would I care? And that's a good question. And so here's the deal. Suppose you drove at 60 miles an hour for 5 hours. How far have you gone? Well, you've gone 300 miles. That 300 miles means something. Okay, again, the idea here is this is a rate, and if I wrote it like that, it would make a little more sense. Miles for every hour. So when I take 60 miles per hour and times it by 5 hours, these cancel off and you're left with just miles, the total amount that you've got done. And that's true for any rate. Your book, and quite honestly, I think most books, spend a lot of time talking about velocities and displacements, which that's because it's an easy thing to grasp. But there are other things for that. You could talk about how fast you're spending money. You could talk about, if you're a baker or something, how many, or like you worked at the big saltines manufacturing plant, how many boxes of saltines are being produced per hour, kind of a thing. And it wouldn't be constant like this, right? It's not going to be constant. Constant's nice, but constant's boring. So in the real world, situations like this, okay, where some goofy shape like this, and how do I find it? Well, this is where we use the integral for, but we'll still be finding an area. Something that I find interesting about this is that an average person can just take and go, well, if I drew a line across here like so, shoot, I could just about, maybe I drew that a little bit too high, but I could cut this bit off up here and like fill in the gaps down here. And it looks like I cut it up a little too high. So someone might be said, well, Jay, I think you made it too high. What if you made it down into here? Maybe you made the height about here. And I don't know. Let's try that. Anyway, you could cut this upper bit off and fill in these low spots and then fill in the box. And then that's an interesting question. So we're going to talk a little bit about that. What I refer to as the average value of that function. Now, the book calls it that too, but they don't talk about it in the same way. So later on, we'll talk about how do you find the average value of a function. Well, it's very easy to do. But in reality, if a person could find that average value and then multiply it by the width across here, you would have just, in essence, found the area of this function. All right, and you would have found the area under it by making it and turning it into a big rectangle, in essence. Okay, and so if you can kind of picture that, I think that's an easy way to go about it. Now, in this first section, what we're going to say is, well, what a person could do to find these areas is they could draw little rectangles under them. Okay, and if my pen would work, it would be handy. There we go. And you'll notice that my rectangles are hitting on the left side of the rectangle. Do you see that? And that's pretty close. And so I've done 1, 2, 3, 4, 5, 6, 7, 8. And so I will, when I'm finished with this problem, have L sub 8. That's how your book writes it. L meaning the left-hand sum or the left sum. You could go back through that same exact picture and draw the right-hand sum. Notice that my rectangles now, the red ones, hit on the right-hand side. In other words, the idea is I need to find the area of these rectangles. I will find where they hit on the right side, like so, and I'll add up those regions. The idea being, again, is the sum of those rectangle areas is approximately the sum under the curve. And you can see that's a lousy estimation because there's a lot of area that won't be counted. Either I didn't count it with the red right there, or I over-counted it with the black. In either case, a person has to be a little bit careful of this. So in this first section, we're going to spend quite a bit of time discussing these ideas of what are called the left and the right sum. And then Also, another one called the midpoint sum, and I'm going to sketch it out for your entertainment. You can all laugh at me. This is why I don't teach art, by the way. I'm kind of lousy at art. The idea here is that my box, the height of it is measured in the middle of the box. You see that? The difference being is on the previous side, the height was on the side of the box or on the other side of the box. In this case, the height is measured in the middle of the box. And again, that's kind of a lousy one, but you get the idea of it. Okay? Everyone see that? So here we'd have the 1, 2, 3. I made 6 rectangles this time. That would be the M sub 6. That's what your book would refer to that as. Now, if this was x equals b over here, and this was x over here, it was x equals a. They're how far apart? Well, they're b minus a apart. You with me on that? And if I divided them by 6, I would say that that is my delta x. Or in other words, that is the width of each of the rectangles. Does that make sense? Okay, so in general, delta x, or the width, will be the same for each one of these guys. I mean, I am not in the big habit of using a different width. I mean, you could, but that's weird. We will mention that a little bit more, I think, in the next section. But in general, we use the same width. So b minus a over n, that is my delta x. Okay, and so one could see you could do a better job if you took and put in more rectangles. The more rectangles you use, the less wasted space there's going to be. In other words, check this one out here. Wow, Jay, that's a good one. There's not much left over. You're right. And so the idea here is as n gets bigger, or we say as n approaches infinity, we get a better estimate. A better estimate of area. Okay, that's fact. And in fact, that is one of the 2 definitions of what you could say for the integral. It is the limit, the integral, which I'm just going to write it as the integral for right now. Later on, we'll come back and define it a little bit better. The integral is the limit of the sum of the rectangles as n goes to infinity, or if you prefer as the delta x, which is, remember, delta x is this thing. As n goes to infinity, delta x is headed to 0. In other words, the widths are getting smaller. Either you're going to have infinitely many rectangles, and by the way, if there are infinitely many of them, they're infinitely narrow. Okay, they're very, very narrow. And the idea is that as you're getting that way, there's going to be less and less and less wasted space. So that's kind of in general. If you can kind of keep that in your mind, I even convinced my dad of that back in the day. We were sitting around one time. Of course, he thought I was dumb to major in math. Big surprise. And we were talking about some of that stuff, and you know, he's like, and I said, well, I do a picture for him. I'm like, so how could you do better? He's like, well, you could make more rectangles. I'm like, literally, that is the definition of an integral, Dad. Good for you. And so he was like, oh, that kind of makes sense. I said, well, good, because math's supposed to make sense. Okay, if math's not making sense, either you're in some weird abstract algebra, which I will admit doesn't make a lot of sense unless there's an application for you to hang your hat on, or you're doing it wrong. Someone's doing it wrong. They're not showing it to you correctly, because math is ultimately the most sensical stuff on the planet. Okay? Now, let's make up an actual function this time, because that's what I do. Here is the function x squared plus 2. Okay, and I want to find, and I'm going to call it y, but remember, if you think about this, this is our f prime of x. Okay, you with me? I want to find the area under this curve. And I want to do it from 0 over here to 4. So from x equals 0 to x equals 4, I want to know what is this region under here. That's what I'd like to know. Okay? And I'd like to do it first with, let's say, 4 rectangles. Okay, so let's do that. I'm going to get rid of this in here, so I'm just going to think about this for a minute. So our delta x is going to be equal to 4 minus 0. Oops, that's 40. 4 minus 0 over 4, because I want 4 rectangles. That means that they are each 1 unit wide. So I'm going to start with the left sum because I feel like it. There's absolutely no rhyme or reason to why I did that one first. If you want to start with the right first, you knock yourself out. And so forth. Okay, there's 4 little rectangles in there. Can you see that? Notice that the height of this rectangle is, well, it's f, well, I'll write this way, it's y of 0, yes? And of course this one here is y of 1, and of course that one there is y of 2, and of course this one here is y of 3. So if you think about it, the sum of the areas is equal to, well now each one of them is going to be, so it's y of 0 times delta x plus y of 1 times delta x plus y of 2 times delta x plus y of 3 times delta x. So a couple things stand out to me first of all. First of all, I see that they all have a delta x in common, so I'm going to take that out. Okay? And so I'm going to rewrite it as this. Oops. Like so. Okay? And now I'm free to go ahead and compute this guy. So I'm just going to be y. So it's going to be 1 times. Well, when you put 0 into there, you get 2. If you put 1 into there, you get 3. Oops. Put 2 into there, you're going to get 6, I think. And you put 3 in there, you're going to get 11. Is that true? Again, we'll plug them into this function right here. So that's 5, that's 11, plus 11 is 22, times 1 is 22. And we say this is L sub 4 for this guy. Okay? Now, let's do it again. Let's do the right sum this time, just for a good time. So here's my function again. But this time I want the right sum. So what you'll notice is the right sum is bigger than the curve the whole time. You see that? Now someone might say, well, does that mean that the right sum is always bigger? No, it has to do with whether the function's concave up or concave down. In this one it's concave up, so right will overestimate, left will underestimate. We'll talk more about that as we go. One can see that if it was concave down, that is, it opened down like this, then the left would tend to over approximate and the right would tend to under approximate. Okay? But it really just depends, and so we'll talk more about that as we go. Notice that this time I have the heights are y of 1, y of 2, y of 3, and y of 4. Sweet! So again, it is the right sub 4 is equal to, again, they're all going to have a delta x, we know that. And it's just going to be y1 plus y2 plus y3 plus y4. And so, of course, that's 1. And you're going to go, well, aren't these the exact same numbers as last time? Yeah, they are. So remember, our equation is y equals x plus x squared plus 2. And so that's, put a 1 in there, you get 3. Put a 2 in there, you get 6. Put a 3 in there, you get 11. And now this guy is new. 16 to 18. So that's 29, 32, 38 times 1 is 38. So R4 is 38. Remember, L4 was equal to 22. This one was underestimating. This one was overestimating. You can be sure that the real area is somewhere between the two of them, yes? And we're going to get into that more later on in terms of, you know, what would happen if I increase from a sample set from a set size of 4 to a set size of 15. I'll tell you what, one thing that'll happen. If you do that, you will end up getting, obviously, better results, and these two will move towards one another. This one will get bigger, this one will get smaller, and they will come in and they will approach the actual real area. Okay? Now let's do a midpoint just for a good time. Same function, because it's easy. And so here it is again, like so. But this time, think about that. That first rectangle, its height is not going to be at 0 anymore, and it's not going to be at 1 anymore. It's going to be at half. Well, how are you going to get a half? Well, you're going to take 0, that's our initial value, so I'm going to write it as A, plus delta x over 2. So in our case, it was 0 plus 1 over 2. That was our first midpoint. First midpoint. Now, how do I get to the second midpoint? Well, that's over some delta x. Are you with me? So if I start here at 1/2, the next one's going to be 1.5, 2.5, 3.5. So this time it's going to be delta x is still the same. And so it's going to be delta x times y of 1/2 plus y of 3/2, that's 1.5, plus 5/2, that's 2.5, 7/2, which of course is 3.5. Now I can't do that in my head. I don't know about you. You're probably better than me. Well, I trust you are. You're better than me. Good for you. So what I'm going to use is a little program that I use all the time in the computer. It's called Desmos.com. Let me pause real quick. Okay, so here it is, Desmos.com. Highly recommend this computer program, x squared plus 4. It is a free program. And, you know, it doesn't cost you a dime. Use it online. Yes, you'll be able to use it for the tests. What I like to do is, if I'm going to evaluate a function, I just go 1.5 right there. Boom, 6.25. Do you see that? That's the y value. To me, that's probably the easiest way to go about this. There's other ways. I'll show you another way or two here in a second. And then just change it. So I'll go back here and make this 2.5. And then touch it. And then it's 10.25. Bam. 10.25, you dummy. And then, oops, what did I do wrong? Oh, you see what I did wrong? Do you see? Some of you already laughed at me, didn't you? That's mean. Don't laugh at me. You triggered me. I forgot one, didn't I? 4.25. So 4.2. I should do them in the right order. Someone's gonna get angry. I'm sorry. Don't hate me. What did I say the last one? Oh, I better start over. I'm gonna mess everything up. Well, I already messed it up. 6.25 and then 10.25. There we go. 6.25. 10.25. There we go. And then, of course, 3.5. Bam. And just click and drag this screen up there where you can see of it. Boom. 16.25. And this is just another way to do it. I kind of dig it. It makes me happy. So if you look, that plus that is this plus this is 26.5. This is 32 and 3/4. And this would make 37, I believe. Okay, 37. Now, interestingly enough, go back and look at our very last one over here. Maybe I need a calculator. So Desmos actually functions as a calculator too. Maybe I'll use it to actually add here, because apparently I'm no bueno at adding today. 3 plus 6 plus 3, plus 6. Yeah, it's 38. Okay, so let's try this again. Oops, let's try it with the other one here. So 4.25 plus 6.25 plus 10.25 plus 16.25 is 37. Well, somewhere I added something funny. Maybe it was the other one. No. And we're back. As you notice, some of you were laughing and pointing at me. I put in x squared plus 4. This is why sometimes, but not rarely I do, sometimes I miss teaching in the classroom, because stupid mistakes like that tend to get caught quicker. Just in general, they do. And so, in general, you don't make as many dumb mistakes. What I was concerned with is 22 and 38. The midpoint should lie not right in the middle of them, but it should be a lot closer to the middle of them than right next to that guy. That was troubling me, and that's why I went back and redid it, because I knew I had messed something up. And so here they are, 14.25. Let's just double check them. And 8.25. I think I already had that. And and 8 1/4, and then 4 1/4. Yep, and then 2 1/4. Good. So if you sum that mess up, let's try it again. So that's this plus this is 6 1/2, and that's 14 3/4. It's 15, and then 29. Hey, look at that. Does that make you happy? That makes me pretty happy. Notice that it's not the same distance from both to both. It's not supposed to be. But it is more or less right smack dab in the middle. So what we'd say then is our M of 4 this time is 29. Okay? So we'll do some more. Of course, that's not a problem. I totally like that. Now, something that I rather enjoy doing, and that's just because that's who I am, I like a spreadsheet. If you don't like spreadsheets, I hope to fix you of that problem. If you think they're boring and mundane, you're wrong, pal. They're awesome. Gosh, help me, I love them so. So what you can do, I'm going to put 0 in here for a good time. And I'll show you what I want to do here in a second. But like right here, I can just go equals. I want to take that thing right there. That's my x. And I want to square it. And to that, I want to add 2. Okay? And what I'm going to be doing here is filling out a table. Okay? And so the first time, you recall, I always went 0, 1, 2, 3. Right? And I could type that in. It's kind of a giant pain in the butt. Okay? So what I will do oftentimes is here. I'll go equals the previous one plus my delta x, which in this case, my delta x is just 1. And then I just click and drag it down. Okay? Now, obviously, it didn't change anything this time. But watch what happens if I change this first cell. Boom. It automatically updated because this cell right here took what was ever in the first cell and added the delta x to it, or 1 to it. Now, you can even get fancier than that, for instance. You can do 0, 4, and then 4, where this is A, B, and N. And then down here somewhere, you could say, well, here's my delta x. It's equals, parentheses, B minus A divided by that guy, by N. And it's 1. And so then, if for some reason you decided you wanted to use 100 instead, boom, it updates. You see that? That's pretty slick. Now, I'm going to do this. Now I'm going to come back in here, and instead of doing +1, I'm going to click on this cell right here, wherever I had that delta x. Now this is important. If you've not done much with Excel, you don't know this. I don't want this 1 right here where this red box is. I don't want it to change. I want it to stay put. The way to do that, if you hit your F4 button on your keyboard, the double dollar signs show up. If you don't have a keyboard like that because you're using an iPad or what have you, and by the way, anything that I'm showing you today can be done in Google Sheets or OpenOffice, Excel, or whatever it is you happen to have. None of that's any different. But if you don't have an F4, you can literally just type in $F, $4. What that does is when you click and drag now, okay, it brings it down. Now, you said nothing happened. Yeah, it did. Watch this. What? That's right. The 89 affects this cell here. This cell here affects this one and all of the rest of them as far as that goes as well. You with me? So just be aware of that as we go along. Now, what the person can do, if you go to the Home tab, you can just hit Autosum right there. If it doesn't auto-sum the numbers you want to add, you can just click and highlight the ones you want to add. And it's 38. That was my first one. Notice if I change this to 0, boom, there's my other one. Yes? Now, you're like, well, what if, Jay, I wanted to start at, what if I want to do midpoint? Can I do that? Yes, you can. So you could do it a couple of ways, but you could say equals this one here plus this guy divided by 2. Are you with me? That would give me my first midpoint. Then all of the rest of the midpoints would be calculated based off of that. And so to me, that's just a fast way to do it. It's a lot of sugar for a cent for like 4 or 5 data points. But as soon as you start saying, well, as soon as you do 4 or 5, you're like, why didn't I just do 100? And my answer to you is, I don't know. Why didn't you just do 100, right? So what I'm going to do here is I'm just going to give you a little something, a little hint of what's to come. And because that's who I am. And I'm going to go back to 0 here just for a good time. Okay. Notice where I left off now. I only went down here to 0.12. Well, Jay, if you want 100 boxes, don't you have to go down to 100? I feel like you do. So, boom, right there. Nice. Oops, come back up here, you hippie. Now, this one here. Whee! Of course, if you knew this, you can double click it and it would copy it down too. If you didn't know it, just drag it down with your mouse. Yay. Here's my question to you, friends. Notice that when I did all this, what I want to do for the right sum, is what I want to do is I want to take and add these guys up, yes? All but the last one. All right, so if you recall, the very first one we did the 0 plus 1 plus 2 plus 3, and we stopped. We didn't include 4. Are you with me? So the same thing will be true here. I'm just going to say equals sum, and it's going to be B1 colon, you can just type it in, or you can click and drag if that makes you happier, to B99. If you go down there and look, you'll see that I stopped one short of, oops, should have been B100 there. What happened? Oops. Okay, B100. Sorry about that. B100. That's why you always check it. Okay. And then we need to times it by delta x. Now remember, our delta x isn't what it was before. Our delta x was 1 before. And so, you know, whether we times by it or not, it didn't change anything. This time it changes something. And you're like, whoa, 29? That's really close. You're right, it is really close. And so left sum is very similar, of course, except sum. This time we don't start at the first one, we start at the second one, right? We didn't include 0 last time, if you recall. We did it by hand. So I'm going to go to 101. And again, it's always a good idea to check yourself. Go down there to scroll down to the bottom and see if that's right. Yep, that looks right to me. Boom. Look at that, 29.65. So you're saying, Jay, that somewhere between 29.01 and 29.65, the true area lies in there. It's exactly what I'm saying. Good job. Good job. It's exactly what I'm saying. And so you're like, well, what if I did 1,000? Then I'm telling you that this 29.01 would get bigger. I'm telling you this 29.65 would get smaller, and they would hone in on the actual area. That's a big deal. It's not hard, but it is a big, big deal. If you keep that in your mind, because what we did there, we let n get bigger, and we let our delta x get smaller. And we said, let's just keep doing that. We could keep doing that forever and ever and ever. And you would see that they'd get to the point where they basically the same. And that's exactly the definition, if you recall, of a limit from 251. That's a big deal. Okay, so we're going to do another one of those just for a good time. So let's just say y equals 3x plus 2, let's say, for instance. And so it turns out 3x plus 2 looks kind of like this, yes? That's a straight line in case you're wondering. If you're playing along at home, it totally is. And let's just for a good time say that we go from x equals -1 over here to x equals 14 because we can. Okay? And so our delta x would be equal to 14 minus a minus 1. That's a distance of 15 divided by how many boxes does a person want to use. I want to use 10 this time because I feel like it. So our delta x would be equal to 1.5. Is that true? Cool. And so what we'd have to do is this. Of course, if we're going to do the right sum, the left sum first, let's say, the left sum would look something like this guy, yes? Am I right? From here to here. And that is, we'd have a height at -1. Well, if you put -1 into here, you're going to get -3 plus 2 is -1. So that's going to be, so, oops. That's not what our picture looks like, Jay. Oh, shit. All right, we'll get into that in a minute. Let's don't do that this time. I didn't want to open that kettle of fish this time. And there's a reason for that. Because that was the next thing I wanted to do. So let's start at 0 again just for a good time. We'll get into that one in a second. Okay. 1.4. Okay. If you plug 0 in here, of course, you get 2. Okay. So if you think about this, in essence, what you're going to have is this. You're going to have an x's and y's. So the first x will be at 0. Then you're going to go over a delta x. Well, that's going to put you at 1.4. Are you with me? So this is going to be y of 1.4. And then you're going to go over another 1.4, which is going to put you at 2.8. And then another one. And then another one. And so forth, yes? This looks like a job for Excel to me. Now, again, for some of the easier ones, you're like, it's just easier to do it on a computer. I mean, it's just easy to do it on my little handheld device. Well, good for you. Good for you. Good for you. Go ahead and do that. I will not argue with you about that at all. If you want to use some combination of tricks, you can go right ahead. I don't care. And then you can just keep doing this over and over and over again. Okay? To me, as soon as I have learned about Excel, there's just no going back. There's just absolutely, in my mind, no going back. So this first one, I'm just going to go, let's go up here and let's put in our values. So we know that our A and our B are 0, 14, and I said I wanted to use 10. So down here somewhere, and it's not real important where, just find a clean spot to work. It's B minus A divided by N. Boom. And so here, it's just going to be equals the original one. All right, we didn't change that. And then it's going to be equals that person there plus the delta x. And we're going to drag it down. We know we have to drag it down to 10. Oops, what just happened? Oh, look what I did. Practice what you preach, Jay. I forgot to put the F4 right there. Are you with me? Okay, notice what happened. When I didn't do that, when I drug it down, look what it's doing. It's adding 0. Okay? Now if I paste it down, now it will change because every time we're going back to that 1.4. That's what the dollar signs do for us. So remember, our function is equal to 3. This is important. It's 3 times x. You cannot just write 3a1 like that. It will not deal with it. It freaks out on you. Plus 2. So there it is. So our sum for our left sum is equals the sum of these ones times our delta x. So that's for our left sum. Now for our right sum, it's the same basic premise, except I want to take these ones times our delta x. And so there it is. And again, this is sub 10. That's L sub 10 and R sub 10. Now you're like, well, that's great, Jay. Now here's something I want to show you. I want to find the midpoint. So watch me do this, plus the midpoint divided by 2. Are you with me? So in other words, we're taking half of 1.4, which is 0.7, and we're adding that to our initial value, which in this case happens to be 0. Oh no! Look at those numbers. They changed. Oh, that sucks. Okay, so let's do this. What I always like to do is I like to copy these things. And over here I like to hit, if you don't know about this key, you're missing out, friends. I'm going to hit paste values only. Okay? And I'm going to get rid of this because it freaks me out. Okay? Because these are just values now. They're not related to any of these numbers. They're just values. They will not change now. The way I had it set up before, they depended on these values that I'm going to be changing. And there we go. So now the mid 10, or M10 they call it in your book, is going to be equal to the sum of, notice it's from, not there, it's from this guy here down to there. Be careful. Notice that the 11th one is for 14.7, which doesn't make any sense because that's outside. It's past the 14. Notice our delta x is still the same. And so there it is. Notice that 322 is more or less in the middle between 292 and 351. It's not perfect. It's not supposed to be perfect. It's close. Okay? And so that is the actual answer. And it turns out that in this case, because that was a linear function, it is perfect. But that's neither here nor there. That's how we work these out. Okay? Now you're like, well, wait a minute. What would happen, Jay, if you saw this function in a dark alley? Okay? I'm scared. Don't be scared. I am here to help. And I would like to find the area between 0. No, 0 is boring. 0. Is that right? Minus 1 and 3. Yeah, that'll work. So which I think is this fellow right here. There we go. Cool. And I want to find this region in here between 1 and 3. Are you with me? There we go. I like that. So let's find the volume, or the area, quote unquote, under the curve between 1 and 3. Now here's a question. All the ones we've done previously have been above the x-axis. Interesting. Area below the x-axis is considered negative. Now, there's a reason for that. Okay? If you were spending money at a certain rate, you would have gone in debt. So negative profit makes sense, for instance. Negative displacement, that just means you came back toward where you started from. Negatives are perfectly happy numbers, so please don't discriminate on them because they're negative. How does this work? It works exactly the same way. So notice that if I was doing left sums, this one would have a height of 0 because it hits at 0 right there. Then it would come down and go over. This guy has a negative height, so this is a negative area right there. This one also has a negative height, and then another negative height, and then one more negative height. So I think I want to use n equals 5 this time just because I can. So 3 minus 1 over 5, which is 0.4. That's my delta x this time. Okay? And so it's simply a matter of going back into your Excel. Again, you can go on the graph and look at them. Whatever makes you happy or makes me perfectly happy too. I'm a easy, happy-go-lucky fella. 1, 3, and 5. And so my delta x would just be b minus a divided by n. Yay! And there it is. And so then here I'm just going to say, well, it equals this initial value. That's cool. And then equals that one plus this one. And then if you can remember to hit F4, that's awesome. By the way, don't lock in the A1 because I want that to change. Boom. Okay. And then here it's equals, what was my function? My function was x squared, so x squared minus 4x plus 3. Yay! That's awesome. And so, again, for our left sum, and this would be left sub 5, oops, L sub 5, it's going to be equals the sum of the first 5 times that fellow. And then for our R5, it's going to be equals the sum of the last 5. And that's interesting. That makes perfect sense if you think about it, because the thing is completely symmetric. So it makes sense that they'd be the same. That's rare that that would happen, but it's fine. It did. It's not the end of the world. And then paste special over here. I just get rid of these guys because it's just easier if you right-click on them. Right-click and then just go to clear contents. It just makes your life, I think, easier, but you can do what you want to do. To find that mid-sum, what I'm going to do is go plus, and again, it's always this delta x divided by 2. And now what I'm going to do is take the sum, and again, I'm only adding 5 because it's mid sub 5. These ones here are the ones that are between 1 and 3. Are you with me? Not the 3.21. So be careful of that. And so negative 1.36. Okay. Turns out that actually is awfully lot closer to the real answer, negative 1.28. they both overshoot because in part that function is, notice how it's partly opens up and it partly opens, it opens up over here and then it opens down. So in other words, what you see here where these ones are overestimated on this side, the other way around would happen if I had done right sums. Okay, it'd been the same picture. So that's interesting. Okay, but that's it. So you're gonna be asked to do a few of those. Okay, whatever. That's part of it. We're also going to mention the name of the terminology of monotonic or monotonous or monotonic functions. That is, we would say that they are monotone increasing. In other words, they are always going up. Okay? It may be that they kind of tapered off, but they're still always going up. They never turned and came back down. This one here is monotone decreasing. Never did it ever head back up. Ever. So this is monotone decreasing. Monotone decreasing functions. Okay? And so that's just something that they mention in this section. I think it's kind of a big deal, but it's not that hard either. Now, we are going to go back and we're going to talk about, hey, look at this left sum routine. Left sum and the right sum. And I'm going to start the right sum because I think it makes a little more sense the way it's written out. It is delta x times the sum of fx sub I, where I goes from 1 to n. That is literally what we just did. Whether we did 100 of them, 5 of them, 12 of them, doesn't matter. That's always the way that function works. This one is not too bad, but it's a little weird. I goes from 1 to n. That's typically how it's written. And this is typically written as x I minus 1. This is why we start at 0 when we do the left sums. Because 1 minus 1 is 0. We start in the 0th term. And so that's typically how it's done. It can also be written this way, although most big kids read that as math PhD people freak out when you write it this way, even though in essence they're the same. Okay, it really makes no difference. So that's the left sum. And then the mid sum is typically written this way. What am I saying? Okay, and then this one here. Now, pay attention to this. This is how I would write it. Your book, I think, writes it more like this, where they use J for some unknown reason, and I don't really honestly know why. It doesn't make any difference how you go about it. So they use x sub j plus 1 divided by 2. They're identical. Okay, so whatever makes you the happier makes me happier. Okay. Now, this summation notation, we're going to see a lot more of that going forward. So if you're not familiar with it, rest assured that we'll get you there. Suppose I was going to add up a constant n times. So in other words, 5. What if I added up 5 4 times? Wouldn't that just be 5 plus 5 plus 5 plus 5? It would be. So it would just be 4 times 5. That's correct. So 20. This will always just give you n times c. Okay, so that's like your first rule for dealing with for summation notations. Okay, if you had two functions added together, and your book always writes it as a sub j plus b sub j, but in reality it's just two functions, any two functions, and then j goes from 1 to n. Or m to n. I guess your book uses m to n in this case, but didn't have to. Okay, it simply meant is that you can split these guys apart, and you could add these guys up first of the a sub j's plus this summation of the b sub j's, these are the same thing, which makes perfect sense because it's all addition, and addition is associative and commutative, right? So we'd use the associative property of addition. You add them in any order you want to. And then the last one that your book talks about, it is a big deal. I mean, you really cannot overestimate how big of a deal this is. And I think your book does this again, as I recall. They pull that constant out front, which we did just a few minutes ago. Remember when we pulled the delta x's out? Because it was just a constant, we could pull it out. So once we did that, then we add these guys up first, and then multiply it second. It's the same thing. Okay? It's basically the distributive property. That's basically all that boils down to. So not very difficult. It's pretty easy, as a matter of fact. Now, the only other thing I want to talk about in this particular section is, well, that's great, Jay, but what if I wanted to get really crazy with it? I'm like, I don't know what you're talking about. And then you say, well, I would like to do this. And I says, okay, cool. That's my function, my f prime of x, if you will. And I would like to say, well, let's let my delta x, be sum b minus a over n, which I totally agree with you. But let's just see what happens here. What if Jay said to you, let's let this go from 0 to 10, let's say, just because I feel like it. So then my delta x would be equal to 10 minus 0 over n, or just 10 over n. Are you with me? Okay. So that's kind of exciting, I guess. Sure. So then, well, what would happen then if you think about this? I mean, what would happen if you plugged in some of our values? So in reality, you'd have, remember, let's say at 0, you'd have f prime of 0. Well, that would be equal to 0 squared plus 5 times 0 plus 2. It's just 2, obviously. What if I did f prime of 0 plus 10 over n, right? That is just one time. Well, it'd be 10 over n squared plus 5 times 10 over n plus 2, right? And what if I did, well, f prime of 0 plus one of these plus 2 of those? In other words, it's going to be 20 over n. In other words, I just have this guy and I added another delta x. I get 20 over n. 20 over n squared plus 5 times 20 over n plus 2. And on and on and on and on it goes, yes? If I kept doing this. Okay, well, I don't know. What do you want me to do? Well, what if I summed this all up? And I summed this whole side up. Well, interestingly enough, I could add up just the quadratic portions, just the linear portions, and just the constant portions of these. And when I'm done, I could then add the three of them together. Because remember, if I want to take the sum, I could take the sum of this piece plus the sum of this piece plus the sum of this piece. And the whole point in doing that is to be able to get to an actual value. So what we're going to talk about is, we already mentioned, well, we want to take the limit as this baby goes to infinity, as that n goes to infinity. We'll only be able to do that if n is still in the function. Okay? And so the game is this. You need to know these three cute little steps. So if you're going to take j equals 1 to n, and you're going to sum up just a bunch of j's. Okay? That is, it's just a constant. It's not a constant because it actually changes. That is, in this case, it's going to be 1 plus 2 plus 3 plus 4 forever, right? Up to n. Okay? So then the question is, what would that add up to be? Well, it turns out that it's well known that that is equal to n. And I'll go ahead and write little n. Since I used little n over here, I'm going to use little n. N times n plus 1 over 2. Or, if you FOILed it out, you'd get n squared over 2 plus n over 2. Okay. What do you mean, Jay? I mean, let's say I wanted to sum up the first 50 numbers. Well, that would be 1 plus 2 plus 3 plus ... plus 50, right? What would that add up to? Well, I don't know, but I do know it'd be this. 50 times 51 divided by 2, which is, I don't know, I can't do math in my head. What do you think I am, a math teacher, for goodness sakes? Come on. 50 times 51 divided by 2, it would come out to be 1,275. That would be your final answer. Okay? Now you're like, well, wait, that's pretty cool. Well, what if it was a linear term? Glad you asked. So if this one came, or that was linear, I mean, that was just like, this is very similar to just saying, let's sum up the x's. This is very similar, by the way, to saying, let's sum up the x's. Are you with me? So what if it was not linear, but rather quadratic? What would it sum up to be? That'd be 1 plus 4 plus 9 plus 16 plus ... plus n squared. Are you with me? Turns out that that would be n times n plus 1 times 2n plus 1 all over 6. Or if you prefer, that's n cubed over 3 plus n squared over 2 plus n over 6. So you're telling me, Jay, that the sum of the first 5 squared terms, which is 1 plus 4 plus 9 plus 16 plus 25, which, by the way, this is 25, and 25 is 50, plus 5 is 55. You're telling me that that's 55. That's what I'm saying. So you're saying if I take 5 times 6 times 11, that's from right up here, and whatever that answer is, I divide out by 6, I'll get the same answer. That's literally what I'm telling you, friend. Oh, well, that's pretty easy. I know, right? So then what if it's a cubic? This is where we stop, by the way, but there are more. This is not a class in fancy schmancy algebra. I wish it, I'm glad it's not, actually. I really don't care for that, but whatever. These are as high as I care to go for the most part. And the idea is well, there's a function for all of that stuff. And so what it turns out to be, it's n to the 4th over 4 plus n cubed over 2 plus n squared over 4. By the way, on a test, yes, you will be able to use these formulas. I'll have them written on the board somewhere, so don't sweat that. Okay? It's like, well, what am I going to do with that, Jay? I'm glad you asked. So one way we can find areas is to just actually evaluate, and it's kind of a fun way to do it. And so let me see if I can find a function here that I want to take a look at. Oh, your book has such weird answers. Let's do it this way. Just want a nice example problem so I can say, hey, look at that one. Okay, cool. Let's look at this one. Let's look at, this is number 58 in the text, and it is f of x. And remember, that really is just f prime of x. You with me? Because I'm going to be basically doing the antiderivative later on. But we're trying to find the area under this curve from 6 to 11. Okay? Now, we could do this with a sample size of any size we want. For instance, we could find it with what do I want to say? We could find it with left sums, right sums, mid sums, whatever. Or we could do it this way. We could say, let's let our delta x equal 11 minus 6 over n, which is, of course, 5 over n. You with me? Okay? And so we're gonna take a look at doing it that way, and we're gonna see what's happening here. So just a minute, I gotta do something. All right, I'm back. Now, think about this for a minute. So each of our delta x's is this thing right here. So you're like, oh, I know. So it's delta x times. Now let's just set this baby up as if we were doing a regular old summation problem. So we're going to I'm going to use I because I like it better, but you do you. And then it's f of, here's the deal. What I want to have this happen is I want to start at A, and I want to add my delta x. And I'm going to add my delta x I minus 1 times. Now that's how I like to do it. That's kind of how I like to do it. And it works. It's fine. It's nothing wrong with it. I'm sorry, not n minus 1. N times. I times, there we go. And we're going to go all the way up to n. Okay, it's just like that. That's the way I like to do it, right there. Okay? So then the question is, well, what does that really mean? It means, well, it's delta x, which is, again, 5 over n. What this really means is you're going to have f of a plus, well, 5 over n plus f of a plus 5 over n times 2 plus f of a plus 5 over n times 3 plus dot, 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 dot. And notice what the last one's going to be. It's going to be f of a plus 5 over n times n. Are you with me? In other words, it's going to be that plus 5. Now, what is my a? My a is 6. So 6 plus 5 over n, 5, is, well, it's 11. And that's exactly what I wanted it to be. Now, what is my a? My a happens to be 6 this time. Are you with me? So I'm going to fill this out as I go along. And I'm just going to see what's what here. So I guess I'll leave that as that. Now, I'm going to redo this. So what I want to do is I want to go delta x, which is 5 over n. And I'm going to do the sum. I goes from 1 to n of f of 6 plus 5 over n I. You're like, okay, Jay, but now what? Oh, bear with me, friend. This is getting good. I goes from 1 to n. And so then it's going to be 6 plus 5 over n I squared. Notice it's x squared. Get it? Nice. Plus 7 times 6 plus 5 over n I. Oh, that's nice. Hey, that's nice. And remember, because we have a summation right here, we can break that into parts, friends. And so we could just do the sum of I goes from 1 to n, 6 plus 5 over n I squared, plus sum, and I'm going to pull the 7 out while I'm at it, if that's okay with you. I goes from 1 to n, 6 plus 5 over n I. Oh, that's nice. But you're like, wait, Jay, can't we FOIL this out? My God, we can. Good eye. Good eye. So that's going to be 5 over n. Sum I goes from 1 to n. That's going to be 36 plus this times this is 30 over n. And there's 2 of them, so that's going to be 60 over n I. And then what else are we going to get? Plus 25 over n squared I squared. Nice. Nice. Plus 7. And I'm just going to leave this one alone for right now, if that's okay with you. And it's 6 plus 5 over n I. Well, now I can pass that summation all the way through again, can't I? I sure can. So I goes from 1 to n of 36 plus the sum. I'm going to pull the 60 out. And notice that the n has nothing to do at all with I. Does that make sense? So my function only deals with i's. So in relationship to I, n is a constant. So I'm going to pull that 60 over n out as well. Make sense? I hope it makes sense. Plus, this also is a constant in reference to I. Oh, I see it now, can't you? And so here I'm going to pass it through as well. And so it's going to be, and I could have pulled this out. You're right, I could have pulled the 6 out as well. I didn't. I chose to leave it in because I'm dumb. I guess. I don't know. I have references. People will tell you. 1 to n. There it is. Nice. Now let's do this, shall we? Do tell, what happens if you add 36 up n times? Well, you get 36n, don't you? Okay. This again is a constant. Now what is the sum of a linear term? We just wrote it down a few minutes ago. It's n times n plus 1 over n, I think. Isn't that right? n plus 1. Oh, no, over 2, you idiot. 2. And then this one is just 25 over n squared. And then the sum of a quadratic is n plus 1, 2n plus 1 over 6. And then here we're going to have plus. Now this is going to be 7 times, this is going to be 6n. That makes sense? And then plus 5 over n, and then of course it's n plus 1 divided by 2. Okay, that's cool. It's exciting. Now, let's do some distributing in here. Let's take this one times this guy. Notice that the n's cancel. And notice that this goes into here 30 times. Are you with me? And notice that this, well, we can do some monkeying with it, but I can lose one of the n's here and one of the n's there. Does that make sense? That's kind of cool, I think. And then here, I can lose an n. So I'm going to distribute now. That's going to give me 180, and then n cancel out. And then this times this is going to be 150. There's an n plus 1 on top, and an n on the bottom. See that? And then here, I'm going to get a 25. I have an n plus 1 on top, and a 2n plus 1 on top. Oops, I have 25 times 5. I'm sure that should be 125. Over 6, and then there's an n and an n, so 6n squared. Well, that's awesome. Plus 42. Oh. I have to be careful because notice that this is all inside of this as well. Are you with me? So it's 7 times 6 is 42 times 5 is 210. And then there's an n over an n, so they cancel out, so it's just 210. Plus, and then it's 7 times 5 is 35. Times 5 is 125. No, it's not. 175. 175. And then there's an n plus 1 on top, of course. And on the bottom there's a 2, and then of course the n from out front. So if I didn't screw this up, it's going to work out. It's going to be exciting. It's going to be awesome. Now, do you recall, and I hope the answer is yes. Yes, Jay, I do remember that. Do you remember back in the day when we did limits in 251? I really hope you do. I'm going to go ahead and distribute the numerators on these guys, if that's okay. And, you know, I guess if it's not okay, it's too bad too, I guess. Whatever. So, I'm going to do this one in 2 pieces because I think people will be upset if I don't. So that's 2n and this plus 3n, I think, and then plus 1 over this. This is left alone. Over 2n. That's beautiful. So I'm going to add this, and I'm going to get 390. Are you with me? And I'm going to break these two into 2 pieces, if that's okay with you. And then I'm going to distribute this, and I'm going to get 250 over n squared. And I'm going to break it into 3 fractions. So that's going to be 375n over 6n squared plus 125 over 6n squared. I already did the 210, so I'm not going to do it again if you don't mind. 175n over 2n, 175 over 2n. Now let's take the limit of this guy. I ran out of room as n goes to infinity. That's what I want to see happen here. Well, this one is not affected by n, so it's just 390. So that's cool. Notice that these cancel out. So it's not affected by n as either, so it's just plus 150. As n goes to infinity, this thing goes to 0, so that just goes away. Notice that the n squareds here cancel out. 250 over 6, I'm just going to write it down. It's a constant. I don't know what it is yet, but it's a constant. Notice that this and this cancel out, but I still have an n on the bottom, meaning that this thing As the n goes to infinity, this thing is going to 0, as is this piece. Here, these guys cancel, and I'm left with 175 over 2. And, of course, this bit here is just going to 0. This right here is the area under the curve. In other words, it is, by definition, the integral. And so I'm going to use a calculator to add that up because I'll just mess it up otherwise. So, oops. I almost messed it up anyways because that's what I do. Oops. $669.166. 669.166. Is that what I said? That's what I said. Okay. Now, if you went back to the front of this guy and you're like, could I just approximate that? Sure you can. Sure you could. Suppose you just said, hey, let's let n equal 100 just for a good time. Which, of course, means my delta x would equal 0.05. Does that make sense right there? You see that? Okay. Then you could use Excel, to get a very good approximation. And that approximation should be very close to what we just did with that limit. Okay, so again, over here, I'll just start over again at 6, 11, and 10, I think I said, didn't I? No, 100, I mean. And so equals, parentheses, this minus this divided by that. And so then here just be equals the initial value. Here would be this plus delta x. Don't forget your F4. And then drag it down, of course, all the way until you get to 100. And I think I got to go to 101 if I want to do it right. Voila. Good for me. And so here my function was, now I forgot what my function was. My function, oh, stop it. X squared plus 7x. So equals x squared plus 7 times x. Oops, double click right here, paste it down. Okay. So then if I just do equals the sum, parentheses, and I'm just going to type it in because I'm kind of lazy, so B1 to B100 times my delta x. What just happened? There's a problem with the formula. B1 times B1. There you go, B100. There we go. 666. Ooh. Or let's try the other sum, the right sum. So that'd be B2 colon B100 and 1 parentheses times delta x. Ooh, 669.72. Hey, guess what lies between those two, friends? I think that's our good friend 669. And so it turns out that what we found a minute ago, that 669, it turns out that is the exact area. So it shouldn't shock me that our values that we're using for our approximations, our right and left sums, would be on either side of that guy. It doesn't surprise me in the slightest. Now, notice here I'm going to try my midpoint formula. And then if I just go equals sum, and remember this time you start at B1 and you go to B100. But of course your delta x doesn't change. And you get 1669.165. Friends, that's pretty darn close. That is really darn close. You're within 1/100th, well actually 1/1000th I guess, of the original value, right? So that's really good. And so, it makes you guys feel pretty good about doing that. You feel like, oh, I really did something. Now, I'm going to do one more of these limit ones. Believe you me, these are not fun for me. They're not fun for anybody. But I think they're good for you to understand a little bit more about the concept of the limit. I think that helps a person out. And I think once you understand a couple of them, I think you feel better about them as a general rule. Okay? You'll notice that I'm only going to do you're only going to do quadratics and cubics and linears. And when I say that, that's because we only told you what those values are. And so here's another one. I'm just going to do x squared. No, I'm not either. I'm going to do 2x cubed. 2x cubed minus x. Oh, I'm sorry. 2x squared plus 2x cubed plus x squared from -2 to 2. Okay? And so in general, what this is going to be then is this. My delta x is 2 minus 2, 2 minus a minus 2, try to get it right, over n, which is going to be 4 over n. So I'm going to have a delta x times the sum, I goes from 1 to n, of f of a plus delta x sub I. That's in general what I'm doing. So 4 over n times the sum, I goes from 1 to n, of f of, it's going to be 2 plus 4 over n times I, and I'm just going to continue blowing this up. It's 2x cubed plus x squared. Right? Piece of cake. Now, let's FOIL that mess out, shall we? I don't really want to, but that's what they want us to do. So I'm going to put a big bracket here, and I'm going to do this and pull the 2 out front, I think, because I feel like that might be easier. And then I goes from 1 to n, of course. And then I'm going to FOIL this baby out. So I'm going to do it twice first, because that, to me, I think makes the most sense. 4 over n times I, 2 plus 4 over n times I. So I'm going to get a 4 plus 8 over n plus 8 over n is 16 over n in the middle, I, plus 16 over n squared, I squared. And you'll notice that that's that bit right there. So I'm just going to go ahead and cheat and use that for right now. I needed it anyways. Cool. And then if you take and multiply that through by 2 plus 4 over n I again, you will get 8 plus 32i over n I plus 32 over n squared I squared. And then when you take and multiply the I through, you're going to get 16i over n. Remember, this is not the same I as imaginary I, in case somebody, you know, it's late at night and you're not thinking squarely. It's not. So just remember, remind yourself of that. And then plus 64 over n cubed I cubed. And so that gives me 8 plus 48 over n I plus, what was that, 98 over n squared I squared plus 64 over n cubed I cubed. Okay, and I'm going to go ahead and combine some like terms in this mess just because I can. So 8 and 4 is 12. And I'm going to pull this 2 all the way out front, so it's going to be 8 over n. Oops. No, it's not. No, it's not. Don't do that. No, it's not. Don't do that, Jay. Maybe I'll multiply the 2 back through while I'm doing this, because otherwise I might mess something up. So this is where a person has to be very careful, because that 2 is only on the outside. Is only on the outside of this summation right here. Okay, so I think I'll multiply it back through just for fun. And then you'll see what I mean by that. I think it might make my life easier. Oops, it's going to be 96. Again, if I don't screw it up, it's going to make my life easier. If I screw it up, it's going to make my life a lot harder. But whatever, you can't have everything, right? And this is all the same summation now that I multiplied it out. So I'm just going to go ahead and add it, like right here. Okay, which gives me 20 plus 96 and 16 is what, 112, I think. And then 196 and 16 is also 112. Okay, and then of course you've got this mess. This is the one I look forward to the least, is the cubic functions. They're very, very annoying. Okay. All right, so again, if you add 20 up n times, you will get what? You'll get 20n. Okay? So you're going to have 112n. I'm just going to show this as 2 steps here. And I'm going to leave off the I goes from 1 to n part, just because it gets a little monotonous. Okay, oops. Right? And so, what is the sum of the i's as I goes from 1 to n? It is n plus 1 over 2, right? And this 112 over n squared is, oops, times, and then this is going to be n, 2n plus 1. Oh, come on. Come on, Jay, why is that so hard for you? I have to have them in front of me. I, honest to God, cannot remember that one to save my life. And I don't know why it is. I know it's cubic, but I always forget that part. I always remember it's over 6, but I always mess that other part up. And then this, and then this cubic one is just, it's just gross. And I'm going to use this multiplied version of it, I think, because I feel like it. And I think I'm going to go back and do the other one the other way too. Okay, I think I'm going to go back and change these other guys out as well. So let me just show you that step. This would have been n squared over 2 plus n over 2. And there's a reason for doing that. Sometimes life looks better one way, sometimes it looks better another way. This is a place where this might make our lives easier or not. Not plus, you clown. Whew. Okay, let's distribute, shall we? So 4 over n. I'm just going to leave that out there. Let's combine, let's distribute this stuff in here, shall we? So 20 over n plus, this is going to be 112 divided by 2 is 56. This n and this n cancel, it's 56n. And then this one's going to be, the n's are going to cancel, and I should just get 56. And then this times this, I'm going to be left with 3 goes into 112. Doesn't go into 112, so it goes in 112 over 3, and there's going to be an n because there's one more n here. The second one is going to be plus 56, and the n squareds both cancel, so that's cool. And the next one, it's going to be, 6 does not go into that, I don't think, so it's that over n, because there's an extra n on the bottom. Here I'm going to get 4 does not go into, does 4 go into 128? 32 times? 32? Yeah, 32 times. Good for me. 32n. 64, just 64. And then the last one is going to be 32 over n. Nice. Now if you distribute this, but maybe before I distribute I'll collect my like terms, if that's okay with you. So how many n's do I have? I have 76. Oh, this is gross. That's gross. Well, let's combine our constants first, shall we? We have 56 and 64 and 56. That's 112. 176, I think. And then plus, and then I guess let's do this. That's 76. I need a calculator. I can't do math. Alright, so clear. So it's 76 plus 112 divided by 3 plus, again, we're doing the ones that are divided by n, plus 112 over, or we're doing the n ones, plus 32. Oops. And that's it. So it should be 145.33. That's this one, this one, this one, and that one. We already took care of those ones. So that leaves us with the over n ones. Are you with me here? So the over n ones, these would be the n ones. I just added them up. Okay. And then we want the over n ones. So 112 divided by 6 plus 32 is 50.66 over n. Okay. Now, if you distribute this baby through like that, you're going to get 24 carry the 2 be 30, carry the 3 be 704, I think. That doesn't sound right. Does that feel right? 176 times 4. My God, I'm right. How about that? Then we're going to take 4 times 145 and a third. So 581.333. Okay. Notice that the n here is now on the bottom. The n here cancels off. And then the n here actually, oops, what am I at? Darn it, don't do that. No, go away. There you go. And now I'm going to take 50.666. 50 point, oops, there's some 5s in there, dummy. Times 4 is 202.66666. 202.6666. Not that it matters because it's over n squared. Now what is the limit as n goes to infinity? This piece is going to go to 0. This piece is going to go to 0. And that right there, friends, will be your answer. Okay. And so that's a pretty straightforward way to do it. It's not terrible. It's not too bad. It is a little time consuming. I will give you that. I'm going to cheat on this one, and I'm just going to alter the sheet that I already have up. This is the beautiful thing, one of the many beautiful things about Excel. And so if I've done this correctly, which I don't think I have, I have not, because I didn't change my formula here. Are you with me? So my formula was, what was it, a cubic function? 2x cubed plus x squared. So what you need to do is go change this function. So it needs to be 2 times, come on, give it to me, 2 times, this needs to be x cubed plus, come on, plus, I said, x squared. It only changes the top one, so paste it down. Oh, stop it. Voila. And then this. Oh. Why does that look dumb, Jay? I'll tell you why that looks dumb. Because we only wanted to go. There we have that. There we have that. All right, one moment, please, while I figure out what I've done. Okay, so I've told you that I love Excel. I was not joking when I love Excel. 5.333 is pretty close to the real answer. It's supposed to be 5 1/3 exactly. So, Jay, why were you off so far? Because of one small, stupid little error. That right there is what killed us, friends. You're like, but that's on the first step. I know. It should have been -2. Ah! Which changes what, Jay? Changes a bunch of these signs in here. Are you with me? There's going to be some sign changes. I'm not sure which one's which, but it's going to be changes in signs. That's why it ended up being the way it was. So I'm going to pause for a minute and fix that. And we'll see if it's the right answer. And I apologize for that. That is a dumb mistake on my part. Yeah. You think you'd be able to follow your notes, but apparently not. All right, just for what it's worth, I just went ahead and I'm doing it here again really quick. If you are watching this, good for you. If you decide to like tune in later and see the final answer, I don't really blame you on that. Plus 80 over NI. Sometimes I like to keep mistakes in the program because I think sometimes that we tend to, maybe we learn, I hope, from mistakes. So hopefully you can learn from my stupidity and you'll make it yourself. That's no guarantee. Lord knows that's no guarantee. But sometimes it helps. I don't know. It's very easy to do. You know, by the way, every dumb mistake that a person can make in math, I've made them all. And sadly, I still continue to make them from time to time. You know, you get in a hurry, you know, and you're going as fast as you can, and you're not trying to mess something up necessarily, but things happen. You mess them up, drop a sign somewhere like I just did. That's kind of ridiculous, but it's a little embarrassing. But I guess life goes on. Just be aware that it happens to everybody. So I don't know. Don't panic. Okay. And again, I'm just going to kind of cut to the chase here. So this is minus 12n. We know that. This is plus 80 over n times. It's n squared over 2 plus n over 2 plus minus 176 over n squared. And then this is n cubed over 3 plus n squared over 2 plus n over 6 plus 128 over n cubed. And then it's n to the 4 over 4 plus n to the third over 2 plus n to the second over 4. If you distribute all that mess out, and I think I'm just going to, for the sake of brevity here, I don't know, let's see. I guess we'll just do this. We'll take this times this. The n's cancel. I get negative 48. This times this, it's going to be 320 over n squared. So it's going to be plus 160. Right. And then it's going to be 320. So it's going to be 160 as well. But there's going to be an extra n on the bottom. And boy, howdy, that's going to be nasty. It's going to be kind of gnarly. So I'm going to do this, leave you an n on top. That's going to cancel. This is going to leave you an n on the bottom. I think that's what I want to do. What is 4 times 76 this afternoon? 4 times 176. 176. 704. Oh, that's right. We saw him before. So minus, and then it's going to be 704. And then that's over n, of course. So then this n and that n will cancel. So 704 divided by 3. So it's going to be minus 704 over 3. There's another, as I said, there's an n down here. There was no n, so it's going to be 704 over 2. I'll just leave it as that for right now. But there's going to be an n in the basement on that one. And then this one's going to be minus 704 over 6n squared. Neither of those is going to matter because there's an n in the basement. They're going to go to 0 when you take the n goes to infinity. You take and multiply this n over to here, it's going to become n to the 4th. Can you see that? So this first one's going to cancel. The rest of them are going to end up with another n on the bottom. So that's going to make my life really easy. And then 4 times 128 is 512. 512 divided by 4 is 128. Again, the end of the 4th cancel out. The next one is going to be 256 over n. And the last one's going to be 128 over n squared. And if I've done this correctly this time, let's pray that I did because I am really getting tired of it. It's going to be 112 minus 704 thirds plus 128 I hope. And then that limit as the rest of these go, where n goes to infinity, all the rest of these are going to 0 because they have an n in the basement. And so, let's bring out the calculator and let's just try this and let's cross your fingers. Let's see if I did it right this time. It's hard to say. Yes! 5 1/3. Attaboy. Second time's a charm, dummy. Alright, so there's that. So, hope that helps. Pretty long video. The good news is, if you suffered through this video, it will actually help you out a little bit. So that's what I'm going to end up doing in section 5.2 is we're going to cut to the chase a little bit. So we've already talked about how the limit is the definite integral in this section. So we're just going to kind of talk about it in quick terms in 5.2, also in 5.3. So some of the stuff we've talked about today in this section will actually help us going forward, so that the other videos can actually be shorter. So in the future they will not all be this long. That's a promise.